questions?
How was your week?
Damn.
That's a lot.
And yours?
It was actually good. This was a good weekend, I feel like. Very relaxing.
I don't remember my weekend.
Because you lived it?
No, because I forgot what I had for breakfast this morning too.
It's the advantage to having the same thing every morning for breakfast. All right, well, in the absence of questions, and students, we're missing 3.
I think you are. 3.
Pardon?
It's just 3, I think.
Yeah, so Stephanie, usually late,
Erica, also usually late.
and Abigail, not sure. There might be email messages telling me what's going on. Well, let's just get the quiz out of the way.
Oh, right.
Young versus then before. Slips. We are dealing with a static equilibrium problem. So let's start out with the force diagram.
We have normal force on the ladder, on the top and bottom. We have there's friction from the bottom of the ladder. The friction is this way.
Friction going which way?
There's weight on the ladder. Normal force on the ladder from the dude. Weight on the man. Is the ladder frictionless? Is that really?
Is the ladder frictionless?
Yeah, like, would there be friction?
Not up there.
Okay. That's all I know.
All right. Acceleration.
Of what, the ladder or the person?
Both.
That's fine.
Pardon?
That way.
What?
If it's going up.
All right, so the person's walking up the ladder very, very slowly. Assume his acceleration is, assume he's moving at a constant velocity. Yeah. Ultimately, we care about the ladder. The ladder's not slipping. So, since this is a chapter 9 problem, where's the axis of rotation?
Where is the axis of rotation?
Is it where the person is standing on it?
Right, anyone else? Okay, anywhere else?
Or the very top.
Anywhere else?
Okay, so the axis of rotation beginning. Can the axis of rotation be anywhere on the ladder? Can the axis of rotation be anywhere on the ladder?
Ben?
Can the axis of rotation be anywhere on the ladder?
Oh, yes, and, or, yeah, it's anywhere you want.
It can be, like, it could be.
Oh, so it could also be randomly selected near Pluto.
All right, go ahead and take this.
Okay.
What? Next. All right, so we have the axis of rotation anywhere we want. We want to make the math as simple as possible. First off, if he's in equilibrium, then the normal force and the weight are going to be equal in magnitude, so this is just going to be the weight of the, I believe as Moran put it, dude. Actually, she said normal force from the dude and weight of the man. I'm assuming it's the same person.
Yeah, it's the same person.
All right, so we can get two equations simply from just Newton's second law, straight up, F equals ma. But obviously, we do have to worry about torque here, because otherwise, why bother doing the problem? When you pick an axis of rotation, you typically pick one that's going to eliminate as much torque as possible. So here, we would eliminate two torques. Here, one torque, here, one torque, here, one torque. Here, two torques. Where those two meet, there, two torques. There, two torques. So there are a number of places that potentially make sense. Now, the first one I heard was here.
I rescind my statement.
Okay. The next one I heard was, I think, down here.
Yes.
So we'll take this as our axis. We'll establish our convention. I hat, J hat, and K hat. All right, equations of motion. Because I don't have to break anything up, really.
If we eliminated those two torques, then do we have to include them in the equation?
No,
Okay.
not the torque equation.
Wait, what are we
Okay.
doing?
Equations of motion.
Okay.
An I hat, a J hat, and a K hat equation.
We can start off with.
Okay.
Negative,
Sorry?
negative y sub 2 plus y sub 2?
Wait, can we?
We're looking at the forces acting on the ladder.
Oh, okay.
Friction.
Negative y sub 2 plus friction. And I think that's it.
Equals m-0, which is 0 because acceleration is 0.
If you don't put the equals in there, it's not an equation. All right, next.
Y1 minus weight of ladder minus weight of boy,
Dude.
whatever.
Is he a man or a boy?
We
Make up
don't
your mind,
measure
Mom.
man,
We don't measure.
And the K hat equation, all right, this is the tricky one. This is the,
Wait, I have a question.
Yes.
Why does the J hat have no acceleration? Like, is gravity not an acceleration?
is it in free fall?
But isn't it always acting on it?
Yeah, gravitational force is acting on it. That's the weight of the ladder right here. But the ladder's not slipping. The center of mass of the ladder is staying exactly where it is, so it's static equilibrium.
Why is the normal force of the dude not included in
Because
Wait,
equals
loud,
the way.
please.
Why is the normal force of the dude not included in the JI equation?
Because I know since it's an equilibrium, those two magnitudes are equal to each other, so we just did weight of dude instead of writing what normal force would do. Yeah, if we were doing it, treating this as a chapter 4 problem, I would have written the second equation and done some substituting. All right, so we're doing some torques about that bottom. I know that the torque from these two is 0. I know the torque, an individual torque is R cross F. And so, well, that one's, we don't worry about those. I have 3 different torques here which have to add up. I know that the magnitude of the torque is equal to RF sine of the angle between them. That angle there is theta. So my first one, well, R is the distance from here to here. Assuming it's a uniformly built ladder, that's going to be the center of it. So we'll call the length of this capital L. So I have L over 2 times the force, which is W sub L, times the sine of the angle between them. And I gotta be careful here, my notation is horrible. Because that's not necessarily the same angle as that. This is the angle between R and F, which may or may not be theta. Well, let's draw it out. I know I've got R going in that direction. I have F going in that direction. I know that angle there is theta.
Oh, so
So what is the angle between them?
theta plus 90 degrees.
Did not give myself enough room. Oh, all right, now the next bit is this positive or negative torque?
Can you remind me the definition between positive and negative torque?
The way that our convention is set up here is that if it would cause, if we think about this ladder with a axis of rotation right here, is that force going to cause it to rotate counterclockwise, which would be positive, or clockwise, which would be negative?
Negative?
It would indeed be negative. Next one, negative x times W sub D times the sine of, well, it's the same angle, they're parallel to each other, so the angle would be the same, theta plus 90 degrees.
Wait, why is the first one negative?
Because I
Why is
just
the
asked.
first one negative?
Because it's gotta be going. It's gonna slip this way.
Yeah. Which way is the force of gravity going to cause this thing to rotate about its axis? So it's going to rotate it that way,
Oh, okay, yeah.
into the board, which is the negative direction.
Gotcha, thank you.
And standing on the ladder would cause the same thing to happen. So it's also negative. And then y sub 2, first off, positive or negative torque?
I think that's positive.
I would hope so, because these two are negative. I'm not having positive, because I know the sum has to be 0. Plus the length of the ladder times y sub 2 times the sine of, well, I've got R going in that direction from the axis to where the force is applied. I have y going this way. I know that angle is theta.
So 280 minus theta.
Say it again.
180 minus theta, she said.
And now it's a math problem. Oh, I guess for substitution, then it's a math problem. For what do we have an independent equation? Or where's our substitution going?
Normal force,
Which one?
y2,
What substitution would you make?
mg.
No,
Oh wait, would this be in rotational motion this time?
it's in complete static equilibrium, rotational and linear.
Well, we can,
J hat, that one.
Yes.
To figure out what the normal force is, because.
Alright, substitution phase right now,
Yeah,
not solving for anything yet.
oh, so,
For what do we have an independent formula?
wait,
Okay, we have a formula for weight. What else?
in friction,
Okay. So my I hat equation now becomes U sub S y1 minus y2 equals 0. The J hat equation becomes y1 minus mlg minus mdg equals 0. And the K hat equation becomes negative L over 2 M sub LG sine of theta plus 90 degrees minus X M DG sine of theta plus 90 degrees plus L y2 sine of 180 degrees minus theta 0. Now it's a math problem. Yes, Stephanie?
What's the math in the middle subscript supposed to be?
What, this right here,
Oh, the other
No,
one.
the middle one.
the middle one, that's a D.
Okay.
So K is, the first part of the equation is,
Sorry, that's not equals there. Sorry, you were asking?
so for K, then first term in the equation.
Okay.
Well, set of terms. That's for this, and
That's the torque caused by the weight of the ladder.
okay. And then the next one is the torque caused by like the angle, or not that, to this equilibrium point.
Well, the middle term is the torque caused because the person is standing on the ladder. They're all torques with respect to the bottom corner of the ladder. I feel like
Can you
I'm
write
missing.
that?
Pardon?
Can you write that?
Torque from weight of ladder. WFL. About. Lower corner. This is the torque. Ultimately, I'm gonna put weight of person, of dude. Technically, it's because of the normal force from the dude. If he jumped on the ladder, then it's not the weight we're concerned with here. About lower corner. And this is the torque from Y2 about lower corner.
Okay.
All right, and now the point at which you plug in numbers is up to you. We can simplify sine of theta plus 90 degrees and sine of 180 degrees minus theta.
What's theta in this case? Do I
50
just
degrees.
choose 50 degrees?
50.
Okay.
So,
140 for the first term. Or
what,
sine. Sine
for the first
theta
term.
plus 90.
that would be 130. So we end up with, let's go ahead and stick numbers in. We've got
What's L? Do
big
we
L
have to choose
is the
that?
length of the ladder, it's 15 meters. 15 meters.
Okay. So negative 7.5.
Let's make it simple and put this on Earth 2.
So gravity is 10 meters per second.
Squared, acceleration due to gravity.
Yeah.
So the ladder was 10 kilograms, I believe. So this is minus 100, or equals 100 plus 500. Well, right there, we get Y1, Y2. Let's go ahead and do that. So Y1 equals 600 newtons, and therefore Y2 is 240 newtons.
Where are you getting your numbers from?
If acceleration due to gravity is 10 meters per second squared, drop back one, the mass of the ladder was 10 kilograms, the mass of the person is 50 kilograms. So the weight would be 10 times 10 and 50 times 10.
Y times 10.
Because
Would you rather do 9.8?
Okay. You just right.
That's when I made the comment of, let's put it on Earth 2, that is setting the acceleration of gravity to be 10 meters per second squared. Earth-like, but not Earth itself.
Not sure, what are we trying to figure out here again?
How far up the ladder he can go before it collapses? We're solving for X.
Okay, I just wanted to make sure.
All right, so we now know what Y1, Y2 are. We can plug into this last equation. We'll have one unknown X, and we'll see what we get. I've run out of room here, so I've got